So next, the question arises, what happens with the covariance matrix of our residuals when the residual process is not well behaving like we have here in this picture, but if the residual term shows this clustering where periods of low and high volatility are alternating. So the problem is that in order to write this term here as sigma square times the identity matrix, so if we want to, in order to be able to simplify this epsilon times epsilon transposed, taking the expectation to sigma squared and the identity matrix which has the dimension t, we need to have a well-behaving process like we have here, okay? Because it was required in our assumptions that the variance of epsilon 1 is the same like the variance of epsilon 2 and so on and so forth. So it was required that all the variances, or that the variances of all error terms are the same. Yeah? Only then we can simplify this expression here by sigma square times the identity matrix, and then we can simplify only then we can estimate the covariance matrix of our beta as sigma square x transposed x inverted. Only then we can do that. But what we have here in the second graph, the variance of epsilon 1 is unequal with the variance of epsilon 2. We have so-called volatility clustering. So the question arises, what do we do then? Obviously, we cannot simplify this expression here like we did before. So now let's take this away. Moreover, we are now the topic is now covariance matrix. Covariance matrix. Okay, so obviously, if the variance of epsilon I is unequal with the variance of epsilon j, then obviously we cannot estimate this guy here as sigma square times the identity matrix of dimension t. So if this is the case, this operation does not longer work. This in turn means that our calculation ends here. Yeah? This guy here is basically then our estimator for our covariance matrix, if this is the case. Yeah? So we can define then, our epsilon, this guy here, our epsilon times epsilon prime or transposed, we can define it as omega. And omega is of course a t by t matrix. Yeah? So how does our omega matrix looks like. So there are different, in the academic literature, there are different suggestions how we can compound this omega matrix. Yeah? And one simple solution is provided in a paper from White. It's called the so-called White correction. The paper is from 1980. Think about it. It's 40 years old. White, the White correction. So White suggests that we estimate our omega simply as a big T by T matrix, of course, and on the main diagonal we put the estimated residuals. On the first element would be the squared of the epsilon of the first residual at time t is 1. Second element on the main diagonal is the second residual, the estimated residual at time 2 squared, and so on. So the last element on the main diagonal would be the estimated residual epsilon hat capital T squared. So we run our model, take the residuals, yeah, as we have defined it here. Yeah, we take the estimated residuals and we square each element in our residual vector epsilon and put it here on the main diagonal. Above and below the main diagonal there are zeros. Yeah, zeros. And of course it's a T by T matrix. Yeah. So we calculate this matrix omega and put it here in the middle. That's basically how White suggests to account for this volatility clustering. And there are of course also other methods discussed in the literature, but this is basically the thing that we focus on. And still now, it's now important to note that if we use this omega here as a proxy for the covariance matrix of our residuals, we still assume that the covariance between epsilon I and epsilon j is equal to 0 for all I unequal j. Yeah? This is what we still assume if we use this covariance matrix. Now, another thing that we could think about, so what happens if our residual process, that's here again plot the timeline, and here our epsilon t. So what happens if the residual process looks like this? Yeah? So obviously here we have some sort of autocorrelation going on. Okay? This is not accounted for in this covariance matrix. Yeah? So then we would have obviously some elements below and above the main diagonal. Yeah? And how this estimate for omega, so obviously our omega is then different. Yeah? So, and there's a paper from Newey West from 1987 who propose an estimate of this omega in case of we have autocorrelation going on in the data. But this is what we do not cover here in this course. Yeah? Because in financial markets, obviously, what we rather face in financial markets is this volatility clustering, okay, which basically indicates a dependency structure in the second moment. So if returns would be autocorrelated, then obviously I would not stand here anymore, but be somewhere in the Caribbean Sea and drink my glass of red wine. Yeah. So obviously, the first moment, financial markets are rather unpredictable, but in the second moment, there we have obviously some autocorrelation going on. So in this course, we are satisfied with this omega here, and we will learn how to implement this omega. Now, of course, you may wonder, okay, but how can we figure out, is there any statistical test that basically that we can use in order to so that we know that, okay, our clustering is significant, and obviously we need to address this issue by using this matrix. So this is what we can, that I would like to discuss very briefly now. Yeah, I will take this away now. Obviously, there's a statistical test procedure that we can employ in order to check if the residuals exhibit this clustering, and this is called the so-called Arch LN test. Yeah, which is a relatively important test. But well, nowadays usually people they don't test anymore. Formally, they just use the white correction when they report the t-statistics. Yeah, so obviously it's important for getting the correct t-statistics. Yeah? So let us denote yt as the excess returns of a stock at time t, and we can regress it on a constant. Let's call it alpha plus beta times xt. And xt, let's define it as the excess market return. Okay, let's define xt as our excess market return and yt as the excess returns of a stock. Yeah? We include in this regression model also an error term. Let's define it as ut. Ut is the error term. So how we would estimate this model? We would estimate this model via OLS, yeah, simply, as we have already discussed. We know how this works. Our X matrix in this case has ones in the first column. Second column are the corresponding elements of our market factor from time t is 1 until time t is capital T. So in this case, our X matrix would be a t by 2 matrix. This is a t by 1 vector of excess return simply, and we would then basically again estimate our, let's call it beta hat by x transposed x inverted times x transposed y. So what we would get then is the point estimator. So our beta hat would give us then, it would be a 2 by 1 vector where we have the estimated alpha, and the estimated beta would be the second element. This is what we would get out of it. So what we can do then is we can retrieve the residuals from that equation here, and how do we do that? Well, we know from our linear regression model y is equal with x times our b hat plus u. So our u hat is then nothing else but y minus x times beta times b hat, and this is then our vector, estimated vector of residuals. Yeah? This is also, of course, a t by 1 vector. So obviously this guy here, we can write it also like that. So here we have the elements u hat 1, u hat 2, and so on until u hat capital T. Yeah? So once we have done that, so we grab this vector from this regression, yeah? And what we can do is now we can do in so-called auxiliary regression. Yeah? So we take this vector and we can square each element in this vector and get basically the squared, just the squared element. So we can run a second regression model where we use the estimated residuals. Let's square them. Yeah, this is the estimated residual at time t squared. We can regress it on, let's call it delta 0, yeah, which is the regression intercept term, plus delta 1 times u hat, so the estimated residual from time t minus 1 squared, plus delta 2 times the estimated residual at time t minus 2 squared, plus an error term. Let's denote it as et. Yeah. So now our regressor matrix X looks like this. We have ones like always in the first column, yeah, forgetting that corresponds or that is associated with our estimates for delta 0. Our second regressor would be then the lagged squared u hat, yeah, that we have basically we retrieved it from here. So we would start here at time u hat 2, time t is 2 because it's lagged, then u hat 3 would be the second element, and so on, and our last element would be then, of course it's squared, yeah, okay, our last element would be then u hat at time t minus 1 squared. So our third regressor in our X matrix would be then obviously u hat at time t is 3.